Okay, well, thank you very much, and thanks for inviting me. Thank you all for tuning in. Nice to see some old friends and some new ones. So some of you might have heard some of this story before, but it's an ever-evolving one. So hopefully there'll be some new stuff. So let's just jump straight in. So first, just a very sort of a broad introduction for those who aren't familiar with magmatic sulfide deposits. But basically, I'm sure most of you will know this: magmatic sulfide liquids form, magmatic ore deposits formed by accumulation of magmatic sulfide liquids, immiscible sulfide liquids. And these form essentially when you've got more sulfur around than a magma can dissolve. And so you end up with an immiscible sulfide liquid that gets carried around in magmas as primarily as droplets, sometimes get preserved in rocks, as in this beautiful sample on the right here, which is a sample of globular ore from Norilsk. Let me just make a laser pointer here. Here we go. So a few different ways that they can get made, and there's a few different varieties. So the major sort of the two kind of major categories depend on what the primary product is. So where the primary product is nickel, copper, and cobalt, these generally tend to be sulfide-rich ores, although you can also get relatively sulfide-poor ones, as in the Jinchuan deposit. And then the other kind is very, very platinum-enriched sulfides, where you typically get very small amounts of platinum-rich sulfides forming stratiform layers in layered intrusions. I'm going to be talking pretty much entirely in this talk about the sulfide-rich nickel, copper, cobalt dominant kind. And I'm also going to be talking almost entirely about those deposits which are hosted in intrusions, as opposed to ones which are hosted in komatiites. So that's the sort of the kind of general scope. And this is a sort of big scale kind of a mantle crustal scale picture of a nickel sulfide mineral system, showing magmas generated in the mantle. In this case, this is a plume setting by in honor of this being a lip group. So magma's funneled up through the crust along some sort of pre-existing control, typically at craton margins, and then ore deposits forming essentially within the plumbing at pretty much anywhere in the crust. We can get deposits formed in deep down in the crust, in the mid crust, in the upper crust, and in the case of komatiites, right on top of the crust. So these the processes that form these deposits don't particularly care where they are. The critical thing is that they're being generated by large volume magma events that are transgressing the crust and lithosphere. What this talk is really about, what kind of physical processes are happening to make these ores, and framing that around the main question being, how do we actually make the intrusions that host them? Because as you'll see, not every kind of igneous intrusion hosts nickel sulfide systems. In fact, they're very particular types of ones that seem to. So we'll address that one. I'll also, at this point, so there is absolutely no geochemistry whatsoever in this talk. Absolutely no rocks were crushed in the preparation of this presentation, and there is a bit of physics, but it's physics that a simple-minded geochemist can understand. So not too alarming. I think there's only one equation. So it's really pretty much all I'm going to show you over the next the rest of this talk is pretty much entirely just geology. And trying to understand the fundamental sort of physical geological processes which go into making an ore deposit. So here are the sort of the major component processes. We have some sort of a conduit system, some sort of a transport system that magma is flowing through. We're pumping magma in the bottom. It's pretty well established by most people who work on these things that the way to make these deposits is by getting sulfur out of the country rocks, typically by getting sulfide out of the country rocks, and incorporating it into the magma. So that's sort of step two. Then the next step is then mixing the sulfide liquid, which is generated by that process, with the magma, and that sulfide liquid then scavenges the chalcophile metals like nickel, copper, cobalt, and the platinum group metals. Then the next step, and what we kind of used to think was really the last one, was the physical segregation of that sulfide liquid into some sort of trap site, some sort of accumulation site, where it then solidifies to make the ore deposit. Over the last few years, we've realized actually that's not really where the story stops. And there's a lot of extra stuff that happens after that. sulfide differentiation, migration, recycling, sulfide silicate interactions, and we'll get into some of that as we go along. So from an explorationist point of view, the really important question is what that distance is. How far can we be from the site of assimilation of country rocks to the site of deposition? Do you have to have a proximal sulfide source or don't you? And from a physical point of view, the point of view of developing exploration models, how long does that process take? So or another way of asking that question, what length and time scales do these various component processes operate at? So now I'm going to tease that out a little bit, and I'm going to step out and show an analogy for thinking of these kinds of systems, thinking of mineral systems as dynamic physical systems. And here's an example of one. This is a supercell thunderstorm somewhere out in the Western USA. And it has some similarities to a mineral system in that it's operating on thousands of kilometer scale. It's focusing mass, momentum, and heat into one place. That's what a mineral system does. It's transient, highly localized in space and time. And the main point that I'm going to lead into here, it's composed of a whole lot of multi-scale processes, constituent processes that feed into one another across a whole range of scales. And the example here is right down at fine scale, we have condensation formation of raindrops. That's actually the major energy driver for forming a lot of these thunderstorms. It's the latent heat of conservation of water is what is the major energy driver. And then formation of clouds, formation of thunderstorms, and then at a larger scale, and there's a larger scale still, these things are embedded in atmospheric scale circulation systems, which are continental to global scale. So now the way to think about, or one way to look at how these processes interrelate, is to think about the scale that they're operating at. And basically we have a mixture of raindrop type processes. These are relatively fast processes, intermittent processes operating at small scales. And these combine together up into slow, continuous processes that operate at large scales. So you can think of them in the old sort of Aesop's fable of sort of hares and tortoises. And sorry, I've just got distracting things happening on my screen. Okay, so how are we going to look at these things? Well, one way of thinking about them and looking at them all in one sort of conceptual diagram is this thing called the gessogram, which I name after my former postdoc, Jess Robertson, who introduced me to them. He didn't invent them, but he introduced me to it. This is a length scale, time scale plot. So what do I mean? Well, length scales and time scales are the characteristic distances or the characteristic time periods over which a process operates. And they come in, and then different processes relate to one another. The relationship between length or distance and time is called a scaling law. And we get different scaling laws depending on what sort of process we're looking at. So if we're talking about flow of magmas, it's essentially linear scaling. So if you take a blob of magma and you flow it for 10 times as long, it's going to go 10 times as far. So we get slopes of 1 on these kinds of plot. Oh, I should just, before I get into that, should just point out a few features of this. So this is distance on the y-axis, it's time on the x-axis, and we're going from nanometers to the radius of the Earth. That's something like, I think, about 25 orders of magnitude y, and then it's about 30 orders of magnitude on x, going from milliseconds up to billions of years. So linear scaling processes like magma flow, and then we've also got processes which scale according to diffusivity, so thermal diffusion processes and chemical diffusion processes. And these are related by diffusivities. And the basic rule, this is just the very, very simple scaling rule that applies to any kind of diffusion-driven process. This is the only equation in the whole talk. H is the length scale, is roughly given by the square root of the diffusivity and the time scale. So any process which is dominantly controlled by either chemical or thermal diffusion is going to lie somewhat on or close to one or other of these lines. That makes it a lot easier because we don't have to solve a lot of nasty equations to predict where some of our important processes are going to be. So here, don't try and take all of this in one go. This is a gessogram for some of the igneous processes which are important in the formation of volcanic provinces and what kind of ore deposits that you might form in them. So I'll just point out a few of them. So magma flow, this is flow of lava on Kilauea. Sitting up here, relatively fast process where we've got meters of flow or tens of meters of flow on a time scale of minutes. formation of individual lava flows and flow fields, typically the order of sort of months, and length scales of tens of kilometers. Sorts of processes that happen in magma chambers that show up in things like summit crater lakes in Kilauea. I'll talk about that a little bit further later on. These are processes which happen on timescales of days and length scales of hundreds of meters. Entire shield volcanoes and large layered mafic intrusions. These things form on a timescale of millions of years and hundreds of kilometers. And then large igneous provinces, some of the biggest processes which we see, which are happening again on timescales of millions of years and thousands of kilometers. So now look at some of the sort of faster and more immediately relevant processes. Thermal erosion in lava tubes. That's a process which has been observed in the field to happen at a scale of sort of tens of centimeters and days. Crystallization, just growth of crystals in magmas. Time scale, length scales of millimeters, time scales of days. And then a very important one for us, the time scale of reaction of sulfide liquids with magmas to scavenge metals. We'll come back to that. That's a really important one. It's slower than you might think. And this is something which is happening on a time scale of days on length scales of millimeters. So armed with that, now let's go to what's probably sort of the simplest kind of formulation of a sort of hypothesis for the origin of nickel sulfide deposits. And that's what's come to be known as the conduit model. We can think of it as basically a sort of reaction cell where we're pumping magma in at one end. This is just sort of a kind of a more spatial version of the diagram of the plot I showed you before, of the diagram I showed you before. Magma flowing through some sort of a conduit, incorporating sulfide from the roof or the floor, generating a sulfide liquid. That sulfide liquid drops out and the magma flows on out the other end. So relate that to our little process diagram that I showed you before. And now let's see where this sits on our plot. So, so some of the faster processes, the accumulation of sulfide liquid, so settling of sulfide droplets, we're happening, so we're probably around about here. So it's something on a time scale of hours, over distances of meters. The reaction of sulfide droplets, we touched on that. That's actually quite a slow process. That's time scales of days to equilibrate droplets with the magma. The incorporation of sulfide into the magma, the main control on that is the melting of xenoliths and releasing sulfide into the magma. That has a wide range of scales depending on exactly what it is you're melting, but typically somewhere of the order of hours to days for centimeter to meter size xenoliths. But then the thing to notice here is that magma flow, the length scale of magma flow over these sorts of times is far greater than any of these. So in the time it would take to melt a xenolith, for example, that xenolith being carried in the magma, that magma might very well be flowing several kilometers. In the time it takes sulfide droplets to settle tens of meters out of a flowing magma, that magma's flowed tens of kilometers. And also the rate at which our sulfide is likely to settle out of the magma is far greater, far faster orders of magnitude than the rate at which that sulfide droplet would actually react with the magma to scavenge metals. So there's an interesting sort of mismatch that shows up there. Without going into the details on what underpins this is all in this paper down here if you want to follow it up. But basically magma flows the fastest of all of the processes. The rate of melting of xenoliths is a really important control on generating sulfide liquid. And in fact, it may be that a lot of the transport of sulfides in magmas is not as droplets at all. It's actually in partially molten xenoliths, which are still being melted by the magma that's carrying them. So that's that point. Sulfide droplets settle or segregate much faster than they can equilibrate. So how do we actually, if that's the case, then how do we make ore deposits at all? Well, that's basically the theme of the rest of the talk. And the reason I'm taking you through this, ore formation requires multi-stage recycling in long-lived systems. And you'll see what I mean as we go along. So basically the simple sort of reaction cell model fails. We're looking at a system which involves retaining sulfide liquid in a magmatic system and recycling it through a considerable period of time while we're flushing magma through the system. A way of thinking about it, which first suggested to me by my old friend Reed Keyes, is thinking about it as an elutriation column. And I won't explain that now, I'll come back to it later, but I'll just plant that term in your head. And now we'll move on to the next bit of the talk, which is looking at the types of intrusions which host magmatic sulfide deposits and how they might form. Well, here's a lot of really sort of familiar looking intrusion types. So conventional sort of internally layered intrusions, dikes, a wide range of scales, and sills. That's one of the classic saucer-shaped sills from the Karoo, and a seismic image of a saucer-shaped sill from offshore Western Australia. So these are probably the most sort of familiar kind of geometries. The interesting thing is that with the occasional exception of dikes, which we'll come to a bit later on, none of these things actually really host significant amounts of nickel copper deposits. So we're looking for some rather more sort of specialized kind of intrusion shapes. I'm just going to mention this one in passing, because I think this is a really important point, and that is this is some work from Craig McGee and co-workers published in Geosphere a few years ago. And a really important point that they made, which I think is something that's well known probably in the LIP community, is that a lot of the transfer of magma through the crust is lateral rather than vertical. Now we're all very used, and we all do it, drawing the kind of diagrams in the bottom left here, which some people call the balloon on a stick diagram, where we basically just sort of assume we're generating magma down here, it goes up through a dike, hits some sort of intrusion vertically above it, and then erupts in a volcano. What the kind of work that people who work in sills and sedimentary basins show is that these systems are actually much more laterally extensive than that. A lot of the distribution of magma through the crust is lateral as well as vertical. And in fact, the typical aspect ratio is probably sort of several tens to one. So in all of the diagrams and cartoons I'm going to show you, they're going to tend to be a little bit biased over towards balloon on a stick because it just makes it easier to draw them. But actually, what we should really be thinking much more about lateral transport processes. And I think that's an important thing to understand in this sort of context. So this is a diagram out of a paper I wrote in 2016, I think now, with some co-authors down the bottom there. This was basically just a very sort of crude, simple kind of schematic view of the types of host igneous bodies that host magmatic sulfide deposits. And most of the important deposits that we know about actually form in relatively small intrusions. We know there's some important deposits in komatiites. I'm not going to talk about them, although they share some important features. There's some quite large, but typically very low-grade deposits that occur in these what we might call funnel or boat-shaped layered intrusions, Mirabella, Kavitsa, a few others. I'm not going to say too much about those either, but we're going to go over and have a look more at these sort of small intrusion bodies. And the one which is probably most familiar to people in the nickel sulfide exploration business these days are these so-called chonoliths. And these are tube-shaped intrusions. There are large numbers of them turning up all around the world these days. They've always been there, but people are now noticing them. I have been for several decades now. And the essential feature is that essentially, as I showed, they're tube-shaped. Here's one of the first ones to really be recognized and drilled out. It's Nebo Babel. It's Limoeiro in Brazil. And this is Eagle East in the mid-continent in central USA. And these things have truly remarkable geometries. A large proportion of them that we know about are mineralized. Whether that's actually a real feature or whether that's just a sampling artifact, I'm not sure. The only way you really know you've got a chonolith is if you drill lots of holes in it. You're only going to drill lots of holes in it if it's mineralized. So there may very well be lots of unmineralized ones that we don't know about. This is my favorite one. This is the current Lake Chonolith in Ontario. And thanks to Jeff Heggie from Panoramic Resources for this one, this bizarre snake-shaped body. That's sort of the chonolith lovers chonolith. And here, sort of economically, the most important ones. This is from my original 2016 paper. This is based on a cartoon from Tony Noldrett, the view of the typical Norilsk Talnak body. There's quite a bit of vertical exaggeration on this one. Down the bottom here, this is a rather updated version of it from Marina Yudovskaya. This reflects a very important shift in our view of what these things are, particularly what the Norilsk ones are. And that is basically paying attention to what the Russians have been telling us for decades, which is these things are not flow-through conduits. They're actually closed-ended, closed system bodies. And the front of them the ends of them break up into lots of little skinny sills and frontal breccias and all sorts of complicated features too complicated to go into. The important thing is that although they're tube-shaped intrusions and they're dead ends. So let's have a look now. This is Nova in Western Australia, in the Fraser Zone, Albany-Fraser origin here. This is a cross-section of it from some recent work of ours with Valentina Taranovic, primarily. Two intrusions. The upper one is a bowl-shaped layered intrusion, fairly typical sort of geometry, quite thick. The lower one is a chonolith, quite an unusual shaped one. That's looking down on top of it. That's looking down to where the arrow is there. The green thing there is the intrusion, and the red and orange things are the ore bodies. Now, if we look along that, so we're just taking a look, looking at right angles to the section and looking along the chonolith, it's got this sort of lozenge shape. Here's the sulfides, they're displaced off to one side of it. That's largely a tectonic feature, although a lot of the emplacement of the sulfides into the country rock is actually an original magmatic feature. We'll get to that. We'll come back to Nova. But the important thing to bear in mind here is, again, like we now think of in the Rills Talnach chonoliths, this thing is not a flow-through conduit, it dead ends. And it ends in the same way that Rills one does. It breaks up into lots of funny little blobs and microsills and fingers. It doesn't carry on as a pathway. So, okay, so how do we make these things? Well, there's lots of different ideas out there. This is from a paper by Peter Lightfoot and Dawn Evans-Lamswood only 10 years ago now, where they proposed primarily structural control. These things were hosted by negative flower structures and dilational jogs on major faults. That's a reasonable suggestion for some of them. It's hard to see how you could make something like Currant Lake that way. The other way is, this is a very sort of typical view from people who work on, look at seismic profiles and do seismic imaging of matrix hills and sedimentary basins, that they form as the fingers at the edge of propagating sills, rather in the same way that lobes of lava flows form as discrete fingers that then merge. And that's just incidentally, that link there is to the talk by Craig McGee, Intrusion in Placement. That was the keynote talk for the nickel conference we ran a couple of years ago. That's still available on YouTube. And this is another cartoon from one of those diagrams showing how these things might conceivably develop at the margins of saucer-shaped sills. So it seems very reasonable. There's no doubt these things can form that way and have the right sort of geometry. The problem is that most of our ore hosting chonoliths are not obviously associated with sills. A lot of them are essentially isolated and don't seem to connect to anything at all. So, so that doesn't really sort of answer that question, but let's have another look at another possible way we might be able to make these things. I'm going to lead into that by looking at some of this sort of progression of sort of intrusion morphologies that we can get, some of this sort of spectrum. Sort of sitting in the middle of the spectrum are things which in this original paper I called the eagle Calatonka type. And these are basically sort of elongate funnels or flared dikes with this funny sort of vaguely kind of hairdryer shaped morphology, essentially tubular bodies, but with dike-like projections down underneath them. And it turns out there's quite a number of different ore hosting intrusions look more or less like this. Very often the lower parts of these bodies are occupied by sulfide matrix breccias. They contain these, that is to say, breccias with sulfide forms of matrix, and we have fragments and autoliths of wall rock and chilled margin within them. Very commonly, the fragments inside these sulfur breccias are actually autoliths. They're fragments of the host intrusion itself. That's Calatonka. There's a new paper just out on this by Yajing Mao. And this is the classic, that's sort of the side-on view, tubes, end-on view, this sort of flared dike kind of morphology. And again, lots of breccia-textured massive sulfides, wreathed in net textured and disseminated sulfides with some really intriguing textures in them. But now the next type of morphology I want to look at, which is essentially forms a continuum with that, these so-called blade-shaped dikes. And these were first really recognized by Jim Mangol in the Raglan South region, south of the main Raglan belt. This is actually the Mequilon dike. Jim recognized that these things clearly appear to be dikes at the surface, but Jim recognized that actually they have a they have a bottom to them, and the bottom surface, the bottom trace of the dike actually sort of dolphins up and down through the erosion level, such that wherever it actually appears at the surface is where you get mineralization appearing in outcrop. But this essentially is the geometry. This is an example of one of them. I think this is the Mequilon dike. The massive sulfides accumulated in the tip of the dike and also extending out into the country rock. Where this happens, they're very commonly tectonized and sheared, which has led people to assume that they are actually tectonically in place in the first place. But I'm not sure that's the case, and I'll try and show you why in a minute. Okay, this is Savannah, formerly known as Sally Malay. And this is turns out to be quite a strange intrusion altogether. Again, it's a dike-shaped body. It's a dike which is a blade-shaped dike, which has now been rotated through almost 90 degrees. It's lying on its side. It's got internal layering is vertical. The basal contact is vertical. The ore body is vertical. And again, we get this sort of projection, basically a sulfide dike extending down into the country rocks. The mineralization, red here around the basal contact, is almost entirely breccia textured, and the fragments in the breccia are some country rocks. There are granulite facies, granulite metamorphic grade metapelites and metasamites, but there's also a lot of norite, which is essentially derived from the chilled margin of the intrusion itself. This is an underground photo taken a couple of years ago of this sulfide dike. Big extensive body of sulfide, several meters wide, about 100 meters long, with what appear to be primary magmatic contacts with the country rock. So there's no sign that this was in place as a shear zone. You can see lots of evidence of country rocks falling off into the sulfide and disaggregating within the sulfide. Okay, so a few more. So these things sort of represent a transition between a sort of bladed dike morphology and the more sort of funnel-shaped morphology. These are the Huanshandong and Huanshanxi intrusions in Central Asian orogenic belt in northwest China. This is from a paper which Jim Mongol and I published in 4 years ago now, highlighting the similarities of these. Now, there's a number of these things, and the important thing is that they form a complete continuum from things which are clearly dikes through to things which look like boat-shaped intrusions. So, well, what are they? Well, we think that essentially what's happening is we're looking at the lateral propagation of dikes, and in the conventional sort of terminology, sort of old-style terminology, dikes fill coin-shaped cracks that propagate sideways, upwards, and downwards. And where they hit boundaries between rocks of different stiffness, different mechanical properties, then they tend to splay out into sills. These are some experiments of dike sill transitions in gelatin water experiments from Janine Kavanagh. Thanks to Sandy Cruden for this slide. But the important thing here, which I'm sure doesn't come to a surprise to anybody in this group, but it does often to others, is that dikes have bottoms. These are great places for accumulating heavy stuff, particularly sulfides. So this is a model that we proposed, a laterally propagating bladed dike that hits some horizon within the country rock, which is relatively easily eroded and assimilated, and that then causes the morphology of this thing to spread out and to start to become more tube-like rather than dike-like in response to the erodibility of the country rocks and also to whatever the sort of ambient stress field is and wherever any sort of structural guides might be to help localize the passage of the intrusion. So that's what we think gives us these kinds of geometries. Jim did some modeling on this and looked at what's likely to be happening at the margins of one of these things. His idea was this, that basically the dike chills against the country rock, forms a thin chill zone, but that chill zone is so thin that the sedimentary rock behind it partially melts, becomes very weak, so that parts of the wall spool off and fall down to the bottom of the dike. This is based on field observations on the South Raglan dikes. I should explain. This isn't just made up. This is actually based on observations. So we get sediment xenoliths containing sulfides and fragments of chilled margin spalling off the side of the dike and accumulating at the propagating edge, giving us these types of features that we see at Savannah. A large part of what's governing that is the kinds of structures which develop at the tips of propagating dikes They generate sets of fractures which actually travel ahead of the dike. The magma then exploits those fractures. If there's sulfide being carried here, that sulfide is particularly going to exploit those fractures at infiltration melting fronts, which is what I'm going to show you a bit of evidence of shortly. So, so it may very well be that the sulfide in this kind of setting is actually a part of the eroding agent, which is actually helping to generate and propagate the migration of the magma and infiltration into the country rock. So and there's another one of these things. That's the 22 dike, South Raglan. So well, that principle of the sulfide eroding the country rocks and perhaps even excavating its own trap sites doesn't have to be restricted to sills. In fact, we see evidence of it in quite a lot of places. And here's some pictures from, that's from the Norilsk Taunak, that's in the bottom of the Aug22 ore body, and that's sulfide invading the footwall, the peelite. This is partially molten peelite peeling off and floating up into the sulfide. This is from underground at the Eagle deposit. This is sulfide invading the black shale, and extending several meters down with these very sort of ragged, very discordant contacts. And here's the edge of the shale. It's starting to melt and sort of peeling up, curling up at the edges like an old British Royal sandwich into the molten sulfide. And then here is a spectacular. This is the sort of the grandfather of them, the best one I've seen so far at Nova. And these very, very broad melt infiltration zones where the sulfide is melting and penetrating into the country rock gneiss. And we'll have a little bit more of a look at that in a minute. But just before we do, just to make a quick point about the physical properties of sulfide melts. So, and there's a couple of things to say. Sulfide liquids are very dense. They're also very runny. They've got very, very low viscosities, less than that of water at typical magmatic temperatures. They also have a very high heat capacity. So they're enormously efficient carriers of heat. So, so sulfide liquids in cracks are essentially hot knives through butter. And I think that explains a lot of the complexity of the kind of features that we see. So, so here, back to Nova, this is our proposed mechanism for the origin of the twin intrusions at Nova. We think that they're starting out as a pair of sills, an upper one and a lower one. The lower one carries much of the sulfide. Then the sulfide effectively sort of knifes its way into the country rock and causes this lower intrusion to propagate as a chonolith. Eventually, this kind of seals off, and then magma continues to come in, inflates and pumps up the upper intrusion as a conventional layer intrusion. But all of the interesting stuff is happening down here at the bottom, forming these spectacular infiltration melting zones. And these extend several tens of meters away from the host intrusion. This is a beautiful example of where the sulfide is actually penetrating right along the gneiss. What it's doing is actually melting out the lower melting layers. And then that anatectic partial melt, that sort of migmatitic melt, actually flows back up the sides of these zones and forms these felsic leucosomes, which are sort of sharing the space with the migrating sulfide. It's beautiful examples underground, and you can see this process in place. So this is our garnet paragneiss. Here's a leucosome layer, and you can see it actually being squeezed out of the paragneiss and into the margin of the sulfide vein. So this is how we see it happening. This is in a paper we published in Economic Geology 2020. Emplacement of sulfide-laden magma. The country rocks underneath are extending to accommodate the geometry. We get fractures opening up. Sulfide starts to penetrate into the cracks. As that sulfide starts to penetrate into the cracks, these country rocks are already close to their melting point, so they start to melt. The sulfide essentially replaces the molten silicate, and the molten silicate flows back up the walls to form these leucosomes. And in some cases, we get these almost pure garnet rinds developing up along the walls of the dikes, which are basically cumulates being left behind by the leucosomes being displaced by the sulfide. This is probably one of the best examples that we've got, one of the best examples we can think of sulfide actually creating its own space, melting its way into the country rock. There's also an interesting timescale argument here, coming back to that, arising from the fact that the Nova intrusion is emplaced into country rocks, which are already very close to their melting temperatures. So this is a temperature versus time plot, and this again is a multi-scale logarithmic time plot here. going days, years out to 10 million years here. The intrusion itself is taking somewhere in the order of 1,000 years or so to solidify, but it's only getting down to temperatures which are still within the melting range of the sulfides. And also we think the range at which we start to form peritectic pentlandite, but that's another story. So we generate the sulfides very early on, but then we've got several millions of years while the peak of metamorphism is going on, while the rocks are being pushed around and deforming at the peak of the origin. And then so we're deforming sulfides within their melting range, and that gives rise to a whole variety of spectacular textures, which you can read about in the paper. So again, just to summarize, that this is all about these very distinctive physical properties of sulfide. So let's look at another interesting physical property of sulfide, and that's to do with its surface tension against silicate melt. This is a numerical simulation that was done by Jesse Robertson, postdoc at SARO. Let me just. So I should just back up and I'll explain it as it goes along. So we're starting out basically with a pool of sulfide underneath underneath flowing magma. The little black things here, those little arrows, those are just vectors showing how fast the magma is flowing. And what Jess showed is that basically all you have to do is just introduce a fluctuation into the flow rate. That starts to generate a wave on the surface of the sulfide pool, and that causes the sulfide pool to be entrained into the silicate and break up into droplets again. And the physics of that are very interesting. Unfortunately, he never fully wrote it up. But it gives, I think, an interesting sort of perspective on the point that sulfide liquids, once you actually accumulate them at the bottom of a flowing magma, that's not the end of the story. They're still likely to be very mobile. They're still very likely to be picked up and continue to play the game. And I think that's one of the key insights in understanding how we can actually generate high nickel tenors. So sulfide melt pools are intrinsically unstable. Now I'm going to show you, this is a cross section or sort of a kind of a composite sort of long section of the Voisey's Bay system, published by Peter Lightfoot a long time ago. And I'm not going to dwell on it at all. I don't really want to talk about any of the details. All I want to point out are these black arrows here, which are the arrows which in every interpretation of Voisey's Bay indicate the notion that sulfide is being derived from an intrusion at depth and is then being placed up this feeder dike system, being mechanically placed up and injected into these trap sites like the Ovoid and the Reed Brook zone and so on. And this sort of interpretation that the sulfide is being derived up from below actually has no real evidential basis at all. It simply comes out of the fact that magmas come out of the mantle, and so whenever we draw pictures of magmas going through the crust, we always draw it going up. But as I'll argue in a minute, there's no reason to assume that magma always does travel up through the crust. And in fact, the reason for making that argument earlier on was to make the point that actually most of the time it probably travels sideways. But there's very likely to be a downward component of motion as well. I'll skip over this because I'm spending a little bit too much time on this. So it's an interesting story, but we'll leave it for now. The other point is that because sulfide liquid is very dense, you don't need to add very much of it to a magma before you substantially affect the density of the suspension. Now, the only reason magmas ascend through the crust is because they're buoyant. It's the only thing that's driving them, unless you're very close to the surface and they're vesiculating, in which case you've got a vapor pressure driving it, a volatile pressure. But deep in the crust, in systems like Nova and Voisey's Bay, there's nothing that's causing the magma to ascend other than its own buoyancy relative to the crustal rocks. So that's the density range typical continental crust. You can see here, if you start adding a few percent sulfide and olivine to a typical basaltic magma, you don't have to add very much before you very quickly form a suspension which is denser than the crust. And so there's nothing driving it upward. So a consequence of that is that these kinds of magmas actually are going to have quite a strong tendency to flow back down the feeder systems that they occupy. So, okay, well, where do we actually see evidence of drawback of magma and magma draining back down conduits? Well, in fact, it's a common thing. And here is a really beautiful recent example of it. This is the summit crater Halli Summit lava lake on Kilauea. And this was shot in early 2018. That image was taken actually while I was there. And then all hell broke loose about a couple of weeks after I left. And what happened about 2 weeks after this picture was taken, there was a massive eruption 40 kilometers away down the southeast end of the Eastern Rift, completely inundated the eastern end of the island, wiped out a couple of my favorite swimming spots, and had this consequence. The consequence was that it drained the summit reservoir, which sits somewhere between 1 and 2 kilometers below the summit here, completely drained it to the point where you have a massive caldera collapse. That crater volume increased from 60 million to 885 million cubic meters in a month, deepened by 500 meters. And interestingly, if you look at that volume, that's actually very similar to the sort of order of magnitude volumes you get in ore-forming chronoliths. It's about the same sort of volume of magma involved. So what's happened here essentially is that you've had a magmatic plumbing system which has been tapped at depth. The magma has been drained off in a completely opposite direction, and all of the magma that was sitting within the summit magma chamber and up to the surface here has now drained back down the conduit again to be erupted eventually 40 kilometers away. So it's a massive cataclysmic drainback event. So what I'm suggesting is that these kinds of drainback events might actually be happening regularly in these kinds of conduit systems, and they might actually be the major catalyst for forming ore deposit. So here, and without going into a lot of detail on this, this is the cartoon that was in the 2016 paper for how I think one of these sort of sill dike complexes might actually develop and form an ore deposit. Stage one here, you've got a sill dike complex. You've got a series of dikes with stepovers and offsets, and these stepovers and offsets gradually widen and inflate and start to turn into sills. And again, now the way to think about this is that most of the migration of magma through this is actually sideways, with some up component, but primarily this is magma flowing sideways through a sill dike network, and sills are developing, and sills and chronoliths are developing in this kind of system, according to where the intersections of the major structural weaknesses are. And this is essentially based on the story that Benoit Saumur developed at Voisey's Bay. So this kind of thing at a small scale. This is a beautiful example of a dike offset. And very commonly, these kinds of dike offsets, you often get accumulations of xenoliths and suspended crystals will actually accumulate in these things. They're really good sort of trap sites. So that might be a little sort of microcosm for where we might form an ore deposit. Okay, stage two. So this system is developing. These sort of sill parts of the system are starting to widen and inflate. We're getting country rock assimilation, further sulfide incorporation. Now we're starting to accumulate some of our sulfide in stagnation points. This might be a Norilsk style chronolith here, where it's propagating off into the country rock. It's basically a dead end, the magma circulating in and out, and dumping sulfide in an accumulation point. At this point, our sulfide might be starting to accumulate, to excavate its own trap sites. Sorry, I'm just going to. I've got a little bit of software on this machine, which is going to throw me out and make me do some exercises. So I've just got to mute it. There we go. Sorry, right, there we go. It's my bossy computer interfering in my life. All right, so this is a sulfide accumulation starting to excavate its own trap sites potentially. Unfortunately, I think I was too late. Oh, I'm not. Here we go. Right. And that's a little reprise of that sort of NOVA model as an example of where we think that might be happening. Okay, now at this stage, we've now developed these sulfide pools, which are intrinsically highly unstable. And I've made the point, these are very, very dense liquids. They're very low viscosity. You're essentially trying to balance mercury on a plate in a highly dynamic and unstable environment with lots of motion of magma and lots of seismic activity and what have you. So there's every chance that these sulfide pools are not going to stay put. What they're going to want to do is to flow back down the system again. Gravity is going to be the dominant control, and gravity is going to pull these things back down the conduit. And where that happens, they're likely to be invading their own marginal rocks. This is a really nice example of one of these sulfide matrix breccias. And this one's actually from the Agua Blanca deposit in Spain, where we think this kind of process might have happened. Sulfide from higher up in the system is draining back and invading through intrusion breccias, which are developed within the intrusion at an earlier stage. And that gives rise to this observation that we very often see massive sulfide forming veins cutting and invading its own host intrusion. This is how I see that process happening. And then finally, the final stage, this is sort of the drawback stage. So this is the stage equivalent to the emptying of the Kilauea magma chamber. We've now got a dense slurry of olivine and sulfide within the pathway. There's nowhere in the world this is going to flow up. It's going to flow anywhere. It's going to flow back down. So what it does is it flows back down and chokes up in sort of the choke points in the system. So in the necks of the conduits, in these sort of step over points like the Rebrook zone at Voisey's Bay, and these things are then potentially, if you imagine sort of a dimension in and out of the page of that, these things could be chronoliths, where we're getting accumulation, this formation of sulfide breccias and what have you. So the key thing here being this late stage mobility of sulfide during the magma drain back phase. So this is now, I'll bring back this concept which I introduced or just briefly mentioned a little earlier on, this concept of an elutriation column. Now, elutriation is an industrial process which is used for getting solids out of suspensions. And effectively the way it works is you have a tube into which at the bottom you pump the suspension that you want to separate. So you're flowing upward, but you arrange the flow rate such that it balances the tendency of the particles to settle out. So you then get an accumulation of the particles somewhere in this column, which you can then just basically tap off. So the analogy is that in this system, the suspension is our silicate melt carrying olivine and sulfide liquid droplets and all the rest of it. During periods of upflow, the sulfides can be carried up through the system. That's when a lot of the initial accumulation happens. But as soon as you turn this system off, or as soon as the settling rate starts to beat the upflow rate, the sulfide is going to start to migrate back down again. And that's the stage at which it accumulates and forms the ore deposits. Now, this kind of process can keep happening as long as you're pumping magma through the system. So you've got a couple of opposing processes going on here. You're pumping hot magma in the system, keeping it open, but you're also losing heat to the country rocks and tending to close it off again. And of course, that's sort of the major kind of limiting factor as to how big these intrusions get to be. The reason why they're typically not very big is because they're losing heat to the country rock at a rate that's faster than you're bringing in new heat with the magma that's coming in. So the key thing to forming the ore deposit is you've got to have a continuous flow of magma for long enough to allow these kinds of processes to happen. If you turn off the flow of the magma for more than a few hundred years, or sort of 1,000 years or so, these things are going to freeze up solid, and that's game over, and that's the end of the ore forming process. So it's all about the relative balance of these different kinds of timescales. That's pretty much the end of the story. I'll just go back to this original diagram, amended a little bit to bring in this point about lateral flow. And just to leave you with, just to summarize that these kinds of scaling relationships and the relative rates at which these different component processes happen is really critical to understanding whether you make an ore deposit or not. And that's basically kinetics. So kinetics is a really important part of the process of ore formation. I think that's true for probably any kind of mineral system you care to name, not just magmatic ones. And it's something which we tend most of the time to completely ignore. So what do we need? We need a persistent magma supply in sill dike networks, persistent being the key thing to keep the systems open, to give these systems enough time to upgrade the sulfide and develop the kind of sulfide metal tenors that we need. And that's our sort of elutriation column kind of analogy for how it might happen. That's where I'll leave it, and I'm happy to take questions. Thanks for listening.
Thank you so much, Steve.